Good morning, everyone. Welcome to day two of LinkedIn's first virtually hosted TechCon site engineering blog. Thank you to each one of you for taking time out to be part of it. Before moving forward, let me introduce myself. I'm Manisha Malik and I will be your host today. At LinkedIn, I'm part of Kafka SRE team, which is responsible for managing one of the largest Kafka ecosystems on the planet. So during this entire session, we will share the work that is being done by Site Engineering India team at LinkedIn and the impact that we are making globally. So a quick note for all of you, we will be taking questions after all the talks. So meanwhile, please feel free to drop your questions in the chat. If you have a specific question to be addressed to a specific speaker, please mention their name as well. We will help moderate them. So let's get started. I would like to begin the session by introducing our first speaker, BG Sudhakar. BG is a senior manager in the SRE organization at LinkedIn Bangalore. He joined LinkedIn 3+ years ago and leads our infrastructure SRE teams. He is passionate about people, processes, and technology involved in engineering reliability into large scale complex systems. So, over to you, BG. Seems like BG is facing some technical issue on his side and is not able to join the call as of now. So keeping the let's keep the show moving. And I would like to call our second speaker today. So delivering our second talk would be Ananya. Ananya is a senior software engineer in infra dev team. She has been working at LinkedIn for over 4 years. As part of infra dev team, she works on platform for network flow data as a source for infrastructure observability. Joining her today is Anuj Srivastav, who is also a senior software engineering with the infra dev team. He has been with LinkedIn for almost 6 years now. He has built multiple systems for the collection of infrastructure health metrics that power infrastructure observability at LinkedIn. Ananya and Anuj will cover infrastructure observability at LinkedIn using eBPF. Over to you, folks.
Thank you. Thanks, Manisha. Hi, everyone. I'm Ananya, and I work for the InfraDev team at LinkedIn. So our team is responsible for building various tools that provide observability into the LinkedIn infrastructure. So what that means is that we collect various data points like metrics, logs from different sources in our infrastructure, like the hosts or the network devices or VMs, right? So today this talk will focus specifically on flow data as a source for observability. Right, so we'll start with an overview of observability using flow data. We'll then move on to an introduction to eBPF and how it works. And finally, we will conclude with some applications of the data that we collect using eBPF as a data source. Next slide, please. Right, so let's start with what is a flow. So a flow is a sequence of packets moving through a network from a source to a destination. So let's consider a certain packet that is moving through your network and it is being captured at this particular network device, which is the flow exporter on this diagram. So this flow would be described by its source IP address, destination IP address, source port, destination port, and protocol, and several other header fields. So this flow can be exported by the network device to an external flow collector. So this exporting of flows is done using various protocols, which is dependent on the vendor of the network device. Some examples of these protocols are SFlow, IPFix, and NetFlow. So this exporting of flows usually involves sampling, which means that Let's say that the network device is configured with a sampling rate of 1000. For every 1000 packets that the device is seeing, it will export one packet to the external collector. Right, so next slide, please. So let's say that we have configured various network devices in our data center with exporting flows to an external collector, and we have all of this flow data available to be queried. So there are several ways in which this data can be used, starting with traffic and capacity analysis. So for that, I'll take an example of, let's say that you have an outage in a certain section of your data center, and you want to find out what are the services that are being impacted by this. So for that, what you would do is you would filter out all of the flow data specific to this section of your data center which is impacted, and then you would group it by the port field, and by that you can find out the top services which are being affected, and then you can take actions accordingly to mitigate the outage that you have. Secondly, we have troubleshooting network bottlenecks. So what that means is, let's say that you have a certain network device which is seeing spikes in the network, and you want to find out that what is the host that is causing these spikes in this particular device. So in a similar way, you can filter out the flows for that specific device, and then you can group it and order it by traffic to find the IP that is responsible for these spikes. Lastly, we have peering. Sorry, back to the previous slide. Yes. Lastly, we have peering data analysis. So peering is when let's say there are two networks and they connect directly to each other to improve the throughput and performance of communication between those two networks. So your flow can be labeled by the various parameters of peering, and then you can use this flow data with the peering related enrichments to optimize various parameters of the peering. For example, the cost of the peering. Next slide, please. Right. So now let's talk about some of the limitations of how we currently export the flows from network devices. So one of the first ones is that it is based on packet sampling. So what that means is that at any point in time, we do not have 100% coverage of all the flows in our system. So we cannot rely on this data for actual values of the traffic. We can only rely on it for understanding the trends in our network. Secondly, now that LinkedIn is moving to the cloud, we will not have access to the network devices involved in the cloud, which could export these flows to us. So we need a different separate source for us that could give us the same information, but from the cloud instead. Lastly, the flows that are exported from network devices do not have sufficient context of the process that is creating these flows. So what that means is, let's say if you consider a certain client to server communication, you would have the 5 tuple for this communication, which is the source IP, source port, destination IP, destination port, and protocol. So while the server's port is fixed, and you can figure out what is the service responsible for that based on some kind of a port registry. But on the client side, the port is ephemeral, which means that it is randomly allotted at the time of client creation. So you cannot tie back this particular client port to which process or application has created this client to this service. So to summarize, what we need is that we need a source of flow information, which is not based on sampling, which is available in the cloud, and finally, which can provide us with some process context information as well. So with that, I will hand it over to Anuj, and he will tell us more about eBPF and how it will help us solve these problems.
Okay, yeah, thanks, Ananya. So before diving into how we are leveraging eBPF at LinkedIn, let's have a brief overview as to what eBPF exactly is. So BPF, which is the predecessor of eBPF, was originated from packet filtering in the early 1990s, and it was used in a bunch of tools, most popularly in TCP dump. eBPF, which is extended BPF, is a full in-kernel execution engine, and it is not just about packet filtering. It processes a full virtual instruction set, and it even has underlying infrastructure to support it, like your eBPF maps and inbuilt helper functions. So it was developed to allow user-supplied programs to be attached to any code path in the kernel in a secure manner. So for example, via eBPF, we can add a trace point hook to the kill syscall. So that will allow us to trace any force kill events that happen on this host. So looking at the diagram, so this is what a eBPF program's flow would look like. It has a user space program and a kernel space program. So a user program would generate a BPF bytecode, which would then be loaded into the kernel via one of the available loading libraries. So in the kernel, there's a verifier which verifies for the safety of the program. It would check for things like if there are any unsafe memory allocations, or if there is any infinite recursions in the program. Once deemed safe, this program will be loaded into the kernel. So your BPF program might have hooks into various kernel subsystems via kprobes or trace points, or even to some application programs through uprobes. So now to get this data into the user program, you can use perf events or the inbuilt eBPF maps. Yeah, next slide, please. Okay. Yeah, so now let's talk about how we are leveraging eBPF at LinkedIn. So we've built an on-box eBPF agent, which is called Skyfall. So it is our infrastructure observability agent that uses kprobes and trace points. So our aim with the Skyfall was to have a lightweight, always on and runs everywhere agent that has very low CPU and memory overhead. As the first use case for Skyfall, we added tracing capabilities to it to provide visibility into the network flows. So how this is different from the traditional flow exporting mechanisms that we talked about earlier is that it does not trace each packet, but it traces at a layer closer to the application layer. Hence, the overhead is greatly reduced as compared to the traditional mechanisms. Yeah, next slide, please. Okay, so this is exactly what Skyfall does. It hooks into the protocol specific send message and receive message syscalls via kprobes. And it also enriches some of the TCP flows with session metrics like TCP retransmits, RTT, packet loss. So all these are useful for debugging network bottlenecks down the line. So in the diagram, you can see the flow of data, flow of the Skyfall data. So on the Linux host, we have the Skyfall agent running. So it interacts with the kernel via eBPF and it extracts the flows from there. So whatever flows it extracts, it encodes them into a custom XDR format and then sends them over UDP to our highly scalable and efficient data collection pipeline provided through inflow collectors. So on the collectors side, all these events are then aggregated over a minute to remove any redundancies, and all these aggregated events are then sent into Kafka. Yeah, next slide, please. Okay, so we've ramped Skyfall to a large number of hosts within our fleet, and we would like to share some of the interesting numbers which we saw from it. So on the left, you can see this is the maximum number of events that has been exported by an agent per second. So this 2000 essentially means that there were essentially 2000 unique network flows that were happening on that host at that moment of time. So it's quite a high number. But even with this, the Skyfall agent was able to run with a CPU overhead of less than 2%. Yeah, next slide. Okay, so some of the overall numbers here. So 16 billion per second events are being captured per second from a single site at the moment. And all these events, when collected at the collector, are aggregated over a minute and they are reduced to 2 million per second events. And this is the ingestion rate into Kafka. Yeah, next slide. I'll pass it back to Ananya to discuss on the applications of this data.
Right. Okay. So let's say that now that we have the eBPF data and we have collected all of it and aggregated it together, we can build several applications out of this data. The first one there would be Infragraph. So Infragraph is a service to service dependency graph, which would consume the flows that eBPF exports as well as the process context on both sides. And with that, it would join both sides and create a service to service dependency graph. So using that for any particular service that is deployed at LinkedIn, you can find the upstream or the downstream services for that service. Secondly, we have several different analytics that can be done on this data. For example, if we want to detect any traffic that is moving through different network environments. You can also use eBPF to detect any unencrypted traffic that may be leaving our data centers. And lastly, you can use it to pinpoint network bottlenecks. So we have the different TCP metrics that we collect using eBPF, like latency and packet loss. So we can use this collected data to debug any network bottlenecks. And finally, the agent that we have developed is generic and extensible so that any new use cases can be directly plugged into the same agent. So, for example, one of the extensions of this agent that we are working on is tracing security events from a host. So, with that, I will hand it back over to Manisha. Thank you.
Thank you, Ananya and Anuj. That was truly insightful. Moving on, delivering our next talk, we have Raji Lakshmi. Raji is a site reliability engineer working with Kafka team. She has been working with LinkedIn for more than a year and has been handling feature development related to Kafka monitoring infrastructure. Apart from her daily work, she has made contributions to School of SRE and has been part of community-driven activities from the Kafka team. Today, she will be talking about the great Kafka engine at LinkedIn. A very interesting topic indeed. Over to you, Raji.
Thanks, Manisha, for the introduction. Hey, everyone. First of all, thank you all for joining my talk on the great Kafka engine. In this talk, we'll try to understand how SREs manage and operate Kafka at scale at LinkedIn. Next slide, please. Let's look at the agenda. First, I'll go through the basics of Kafka. I'll be explaining what Kafka is and some of its use cases. Next, we'll look at some important terms and key concepts related to Kafka so that you'll have some context on understanding what follows. Then we'll peek into the scale of Kafka at LinkedIn, what challenges and issues it brings along. And finally, we'll look at some tools and automation we SREs develop and use at LinkedIn to manage clusters every day. Next slide, please. What is Kafka? So Kafka is a distributed message queue. So what is a message queue? So it's a system where messages or events are pushed by services, stored in queues, and then read by downstream applications. Why distributed? The design of Kafka is such that data in a single queue is stored across multiple hosts. In the Kafka world, we call this bunch of hosts together as a cluster. A message queue in Kafka lingo is called as a topic. So I'll be using the term topic, clusters, and Kafka a lot henceforth. Fun fact, Kafka was ideated and developed at LinkedIn. Now we all know that it's open source under Apache Foundation. Now, what are the key features of Kafka? So Kafka is a low latency system. So messages are written to and read from Kafka in the order of a few milliseconds. It's a fault tolerant system. In case a single host in a cluster goes down, it will not affect the overall availability of messages stored in queues in the cluster. It offers durability of data. So it is guaranteed that the message in the queues in the Kafka cluster will stay for the period specified. Like it could be a few seconds, or it could even be a few years. Kafka is scalable. It's easy to horizontally scale up or scale down a cluster without affecting the availability due to how Kafka is inherently designed. Now let's look at some use cases of Kafka. So Kafka is used as a message broker. So it's used to decouple producers and consumers. So it's used for web activity tracking. So user-generated events such as page view events or page click events are streamed to Kafka topics and then processed by downstream applications. It is used as a metrics aggregation platform too. So monitoring data from various upstream applications go into Kafka topics, and these are later consumed for, let's say, displaying graphically, for example. This is not an exhaustive list of use cases, of course. So it is used for other uses as well, like log aggregation, event streaming, etc. Next slide. Now let's go over some key concepts related to Kafka. So these are keywords and concepts that will be used later on throughout the talk. So topics. So the message queues we talked about previously are called as topics in Kafka. So usually topics are created according to the type of events that are produced into it. So you can have, for example, one topic which records just page view events, another separate topic which records page click events, etc. So one topic per type of event. Each topic is constituted by a certain number of partitions. So messages produced in a topic go into exactly one of these partitions. So in this figure on the side, we can see that the topic has three partitions, 0, 1, and 2. So each partition is hosted in a different broker. So what I mean by broker is a host in the cluster. So partition 0 goes into one broker, partition 1 and 2 go into two different brokers. Now, what are replicas and replication factor? So each partition has exactly certain number of replicas. So this number is called the replication factor. So let's say the replication factor for a certain topic is 4. So this means that each partition in the topic has 4 copies of itself, four replicas. So together it has 4, so 3 copies of itself. So out of these 4 replicas, only one of these replicas can take reads and writes, and that's called the leader of the partition. Next slide, please. Producers and consumers. We've seen these terms before. So producer is an application that writes messages or events to topics, and consumers are downstream applications which read the messages and may do some processing on top of it. Next slide. Now we've come to the main theme of the talk, that is the scale of Kafka at LinkedIn. So Kafka SREs at LinkedIn manage around 170 plus Kafka clusters, which together have around 14,000 live brokers. These clusters handle huge volumes of traffic at LinkedIn. At any given day, we have around 17 trillion messages coming into our clusters together. Even as we speak, the volume of incoming messages is certainly increasing. So you can easily see from these numbers that Kafka infrastructure at LinkedIn is enormous. Managing such a huge, critical and central piece of infrastructure brings some unique operational challenges. Next slide, please. Like I said, more the scale, the more the challenges it brings. So as we have increasing volumes of messages coming in, we would need to scale the clusters proportionally to store these messages and service reads and writes. So added to this mix is the diversity of user topic. So some upstream applications may produce bursty traffic, for example, which leads to sudden spikes in incoming messages. Some apps could periodically write messages to the topics, and some applications may produce traffic continuously, such as streaming applications. So all these factors make managing these large Kafka clusters more complex. Next slide, please. Now let's look at some operational challenges we Kafka SREs have to deal with on a daily basis. Broker failures. So broker failures have become more common when we have increase in volume of traffic. So brokers could fail because of full disk capacity, contributed by, let's say, some spike in load into a partition hosted by the broker. Sometimes one of the RAID disks might fail. Sometimes some brokers in the cluster may be network partitioned due to switch failure. That is also considered broker failure. So dealing with broker failures every day is a challenge. Cluster capacity. So we need to add and remove brokers from a cluster on a daily basis. So sometimes we might need to swap a batch of brokers. So replacing a bunch of unhealthy brokers with healthy ones as part of routine maintenance or as a step to mitigate some issues. Managing imbalances. So there might also be cases where the cluster might not be in a balanced state. So when I say balanced, I mean that the load, the incoming load is spread evenly throughout the cluster. So ideally, only a certain group of brokers should not be more loaded than the rest. The load should be evenly spread. In that case, in a case where the load is imbalanced, we may need to intervene and rebalance the clusters. So sometimes instead of load, one single broker could have more leader partitions than the rest. So this is called a leadership imbalance. So the mitigation for these issues, if it has to be done manually, it's very complex. It's a multi-step process and it's time-taking and therefore it's very painful. So this is where we use tools and automation, and that's where tools come to the rescue. Next slide. So one of the important tools we Kafka SREs rely on, like depend on or swear by is cruise control. So cruise control is a software that helps manage most of these operational challenges. So it was created here at LinkedIn with the vision that it should help do away with all the human-oriented mitigation and recovery. Like Kafka, this project is also open source. So we have one cruise control instance at LinkedIn per Kafka cluster we manage. It's designated to each Kafka cluster. So cruise control basically follows a goal-based approach. So what's a goal? So goal is a condition that has to be met. And if this condition is violated, some remedial measures are taken to bring back into the target goal. So for example, disk capacity goal is one such goal, which says that the disk space usage for a cluster has to be below a certain threshold. Okay. So cruise control basically detects things like goal violations, broker failures, and metric anomalies, and puts in remedial measures wherever possible. So these remedial measures could include, for example, say, moving around replicas in a way that the goal is met. In some cases, where cruise control cannot do anything, human intervention is required. So since cruise control knows about the Kafka cluster it manages, it could also be used as a central place to know all about the cluster it manages. So for example, if you want to know what partitions are, which replicas in a partition are down, so how many leader partitions are present in a certain broker, how many replicas are present in a broker, you can use cruise control for getting all that information. So what I've talked about cruise control, of course, does not do justice to everything cruise control can do. So it requires a talk in itself. Next slide, please. So we also use other workflow, other tools to make our lives easier. We use a workflow automation engine, which is based on Commanda, to remove brokers, add brokers, and swap brokers in and out of the cluster. So basically, it kind of prepares a host to run Kafka. It puts the host in the cluster and makes sure that it gets replicas and all the other complex operations that are involved in broker addition, removal, and swaps. In the next slide, I will show you a screenshot of how the cockpit looks like, how the Commanda UI looks like in our, while we manage our clusters. So we also have a monitoring infrastructure specially designed for Kafka. Since Kafka is very critical, it's a critical piece of infrastructure to LinkedIn, we have our own monitoring and alerting system in Kafka. Next slide, please. So this is what I was talking about. This is the workflow automation engines UI. The workflow chart here you see is for a swap operation. It has useful information like tracking the progress of the swap workflow, Maybe you can even pause it or restart it, view what kind of tasks are performed at this stage, and what incidents are associated. Let's say the swap doesn't go as intended, then what incidents are there? And it's a central place where we can track the progress of the operation. And with that, I come to the end of the talk. So hope you all have enjoyed the talk and gained some insight on how we operate Kafka at LinkedIn.
Thank you, Raji, for such an informative presentation. So now I would like to welcome BG again. BG is Senior Manager at SRE Organization at LinkedIn. He joined LinkedIn 3+ years ago and leads the infrastructure SRE teams. He's passionate about people, processes, technology involved in engineering reliability into large-scale complex systems. Over to you, BG.
Thanks for that intro, Manisha. Hello, everyone. Good morning. Hope you enjoyed our very informative sessions this morning. I certainly did. So just want to closing out our session today, I wanted to provide some background information on site engineering at LinkedIn. So at a high level, site engineering is the umbrella org at LinkedIn, which is responsible for our data centers and production environment. We do network engineering, systems engineering, performance engineering, and site reliability engineering. As a company, LinkedIn has experienced nearly continuous growth since its early days. LinkedIn currently has around 810 million members worldwide, data as of early this year, with around 115 million of those being weekly active users. And these members interact constantly with our platform. To provide an idea of the scale that we operate at, we serve upwards of 1 million QPS. And as Rajalakshmi pointed out in her presentation, we send 17+ trillion Kafka messages a day, and we have 2 exabytes of offline grid storage capacity. As you can imagine, to deal with this kind of scale, we need cutting-edge technology and infrastructure platforms. The kind that you saw demonstrated earlier in the session. We expect that these platforms would work seamlessly, they can scale to the demand of business growth, and that they're easy to operate. This is where site engineering and site reliability engineering play a big role. So what we do is we apply site engineering principles. We apply engineering principles in order to make this complex infrastructure scalable, reliable, and easy to operate. And the goal for us is to make sure that every member of the engineering workforce at LinkedIn can easily manage LinkedIn's ecosystem. Next slide, please. So the last 7 or 8 years have seen our growth trajectory get a lot steeper. It took us about 10 years to reach $1.5 billion in revenues. And in the last 8 years, we were adding almost $1 billion in revenue every single year. And while the growth in the last few years has been phenomenal, we expect it to continue to remain strong in the coming years as well. The next few years are going to be very interesting here at LinkedIn, where we will witness both tremendous business growth and accompanying that massive infrastructure growth. And this will create opportunities for each of us to learn, grow, and to create meaningful impact. Site engineering as a function overall plays a very critical role in enabling LinkedIn's hypergrowth. Next slide, please. So a little bit about the site engineering organization. So as I mentioned, it consists of software, network, database systems, and infrastructure engineers. As you can see, we have teams distributed around the world in several locations. We're headquartered in Sunnyvale. There are locations in San Francisco, New York City, and Bangalore. While we have globally distributed teams, we trust each other to do our best work wherever that works best for us and our teams. So in other words, hybrid remote work is here to stay, and we encourage it. Next slide, please. So a little bit about some of the core principles we follow in site engineering. So site up for us is foundational. And it's really quite simple if you think about it. If the site isn't up and functioning for our members and customers, we don't really have a business. In addition, it takes a village, as they say, to run complex production systems. Developers as well as SREs need to own operational problems, and a tight feedback loop between software development and production operations is critical. So we build lots of self-service tools, platforms, and systems, some of which were mentioned in the previous sessions. Last but not the least, we think of operations like any other software problem requiring engineering work, not heroes and raw effort. Next slide, please. So we, at a high level, stepping back, we conceptualize site engineering evolution and SRE evolution and maturity as a journey. And we have an internal scale that looks something like this. And we see teams progressing through multiple phases and the function as a whole also following that progression. So the phases are, firefighter, gatekeeper, advocate, partner, and engineer. And the effort for us is constantly to move towards the right. We've come a long way on this journey, but we have further to go yet. The future is exciting, and we're preparing ourselves to meet the challenges ahead. Thank you very much. And with that, I'll hand things back over to Manisha to wrap up. Probably conclude with Q&A. Over to you, Manisha.
Thank you, BG, for taking us through the site engineering journey at LinkedIn. So now, finally, it's time to feed our curiosity. I'm delighted to hand over the floor to Priyanka, who is working in infrastructure monitoring and visibility space for the Q&A session.
Thanks, Manisha. So, So let's start with asking our speakers some questions about their tech talk. So first question we have for Ananya and Anuj. So the question is that once you capture the event at the source, how long until it can be consumed by users?
Right. Sure. So thanks for that question. From the agent perspective, once it captures the event, we have a 5-second flush interval. So it flushes to the collector every 5 seconds. And then on the collector side, we wait for a minute so that we have received the last minute's flows. We aggregate it and then we send it to Kafka. So it would be at least a minute and a few seconds until the data is ready to be consumed from our Kafka topic.
All right. Thanks for answering that, Ananya. We have one more question for you. And the question is that why are we using UDP for sending flows?
Anuj, do you want to?
So we are just leveraging the existing inflow pipeline for Skyfall. So that was built over Sflow and UDP. So we have stuck with that, and we are consciously trying to keep the message sizes under the MTU limit. So that way, the drops which we are monitoring are not too high on the Skyfall to inflow pipeline, and that's why we've stuck with UDP. But we could move it to TCP. So there's no technical reasons for it, but it's a reason that we already had the pipeline in place and we just leveraged it.
Yeah, thanks for answering that, Anuj. Next, we have a question for Raj Lakshmi. So the question is that why do we have such an enormous scale of Kafka at LinkedIn?
Okay, thanks for that question. So why we have it is because, first of all, LinkedIn is widely used as Kafka is widely used at LinkedIn. So like almost every application we have at LinkedIn uses Kafka in some way or the other. That is one. And we use Kafka for, like I covered in the use cases, we use it for web activity tracking. So, and LinkedIn is also, the user base of LinkedIn is also growing enormously. Like VG said, it's about 800 million members we have at LinkedIn. So imagine having such a huge volume of events generated for each of these members. And you can imagine, how much we have to scale Kafka and how many clusters we need in order to bear that capacity and do processing on top of it. So that's why, so basically to answer the question, so both the usage internally at LinkedIn and the growth proportional to how many members we have on LinkedIn as a platform. So we have Kafka growing according to that.
All right. Thanks for that, Rajlakshmi. One more question for you is that where does Kafka stand at with regards to cap theorem?
Okay. Cap theorem, we discuss cap theorem generally in the context of distributed systems, right? So consistency, availability, and partition tolerance. So Kafka, we can say, is a CA system. It guarantees consistency and availability. So I can say that it's a CA system.
All right. Thanks for answering that, Rajlakshmi. And thank you, Anuj and Ananya, as well. Back to you, Manisha.
Thank you, Priyanka. Okay, with that, we will be concluding our today's session. So before moving on, a small suggestion for the audience to go and check out more about careers at LinkedIn. Our networking booths know more about teams at LinkedIn, and you can always connect with our volunteers too by clicking on the Connect with Booth representative to know more. So I would like to also request the audience to please share your feedback for the event with us by filling the feedback survey by scanning the QR code on the screen. This will help us make the next such events we host even bigger and the better. So thank you to our core team, all our speakers, and everyone who has joined today to make this event a success. Thank you, everyone. It was a pleasure hosting you this morning.